Welcome to the Snoozy Scientist, to today's extraordinary voyage through the corridors of deep time. Whether you're a truck driver navigating the endless highways under starlit skies, or someone finally settling down after a demanding day at the office, you've found exactly the right place to be tonight. This is your sanctuary, your moment of peace in an ever-spinning world. I'd love to hear from you in the comments. Tell me what time it is where you are, and which corner of our beautiful planet you're calling home tonight. The visuals accompanying our journey tonight will paint pictures of wonder and possibility, but they're simply here to enhance the experience, not define it. Feel free to close your eyes whenever you wish. Let your imagination become the canvas upon which we'll paint the future of our world. Sometimes the most vivid landscapes exist, not on screens, but in the theater of the mind. Tonight, we're embarking on a journey that stretches far beyond the brief span of human civilization. We're going to travel forward through 5 million years of Earth's future, witnessing transformations so profound they'll reshape everything we know about our planet. This isn't just about predicting tomorrow's weather or next century's technology. We're diving into deep time, that vast ocean of years where entire species rise and fall like waves, where continents drift like slow-moving puzzle pieces, and where the very face of our world transforms in ways both subtle and spectacular. 5 million years. Let that number settle in your mind for a moment. When we look backward through the same span of time, we find ourselves in the Pliocene epoch, when our early human ancestors were just beginning to walk upright across the African savannas. The Mediterranean Sea had recently refilled after being completely dry for thousands of years. Giant ground sloths roamed South America, and saber-toothed cats prowled through forests that would one day become our modern cities. Now imagine that same incredible span of time stretching ahead of us. What wonders await our planet? What new forms of life might emerge? How will the forces that have shaped Earth for billions of years continue their patient work of transformation? As we begin this journey, let's start with something we can observe happening right now: the gradual but relentless movement of Earth's continents. The theory of plate tectonics tells us that our planet's surface consists of massive rocky plates floating on a sea of molten rock below. These plates move at about the same rate your fingernails grow, roughly 2 to 4 centimeters per year. It seems impossibly slow, but over millions of years, this gentle drift reshapes entire continents. Picture the Atlantic Ocean growing wider with each passing year. Right now, as you listen to these words, North America and Europe are moving apart at about the width of your thumb annually. In 5 million years, the Atlantic will have expanded by approximately 100 to 200 kilometers. That might not sound dramatic, but it's enough to significantly alter ocean currents, weather patterns, and the distribution of marine life. Meanwhile, the Pacific Ocean tells a different story. This vast body of water is actually shrinking as the Pacific Plate subducts beneath surrounding continental plates. The famous Ring of Fire, that horseshoe of volcanic activity encircling the Pacific, marks the boundaries where oceanic plates dive beneath continental ones, creating the mountain ranges and volcanic arcs that define much of the Pacific Rim. But perhaps the most dramatic continental movement involves Africa's inexorable journey northward. The African plate continues its slow collision with the Eurasian plate, a process that has been building the Alps and other European mountain ranges for millions of years. In our 5 million year time frame, this collision will have progressed significantly further. The Mediterranean Sea, that cradle of ancient civilizations, will have grown noticeably smaller, perhaps transforming into a series of large lakes rather than the sea we know today. In the east, the Himalayas continue their patient growth as the Indian subcontinent pushes northward into Asia. These young mountains, geologically speaking, are still rising at a rate of about 1 centimeter per year. Over 5 million years, they could gain another 50,000 meters in height, though erosion will simultaneously work to wear them down. Still, it's possible that some peaks in our future Himalayas will dwarf even Mount Everest's current majesty. Now let's turn our attention to one of the most fascinating aspects of our planet's future: the evolution of life itself. Evolution never stops. It's not a process that reached some perfect endpoint with the emergence of humans. Instead, it continues its endless dance of adaptation, innovation, and change. Every species on Earth today, including our own, represents just one frame in an endless movie of biological transformation. What might happen to humanity over such a vast timescale? This question touches on some of the deepest mysteries of our existence. If we assume that humans survive as a species for the next 5 million years, we'd likely be virtually unrecognizable to our current selves. Consider that the entire span of recorded human history covers only about 5,000 years. We're talking about a period 1,000 times longer than all of recorded civilization. However, the integration of technology with biology presents possibilities that evolution alone never could. Perhaps by then, the distinction between human and artificial intelligence will have blurred beyond recognition. We might exist as hybrid beings, part biological, part technological, with capabilities that would seem magical to us today. Or perhaps we'll have transcended physical form entirely, existing as patterns of information in vast computational networks. But let's not forget about the countless other species that share our planet. They too will be evolving, adapting, and changing. The process of evolution, given 5 million years to work, could produce creatures that would astonish us with their beauty, complexity, and strangeness. Birds might evolve in remarkable directions. Perhaps some lineages will develop even more sophisticated cognitive abilities, creating avian civilizations with their own forms of art, music, and technology. Others might grow to enormous sizes, filling ecological niches left vacant by extinct megafauna. Picture descendants of ravens with the problem-solving abilities of dolphins, or eagles that have evolved cooperative hunting strategies rivaling those of wolves. Marine life presents equally fascinating possibilities. The oceans, covering more than 70% of our planet's surface, offer vast territories for evolutionary experimentation. Whales and dolphins, already among the most intelligent creatures on Earth, might develop even more complex social structures and communication systems. Perhaps some marine mammals will evolve the ability to manipulate their environment in ways we currently associate only with humans, creating underwater civilizations in the deep ocean trenches. Cephalopods, those masters of camouflage and problem-solving, might evolve along paths that would blur the line between individual organisms and environmental elements. Imagine octopi that have become so sophisticated in their camouflage abilities that they exist as living, thinking extensions of coral reefs themselves, or squid that have developed bioluminescent communication systems so complex they amount to underwater cities of light. The insect world, already incredibly diverse, might surprise us most of all. Insects have survived every major extinction event in Earth's history and have adapted to virtually every habitat on the planet. Given 5 million more years, they might evolve forms of collective intelligence that dwarf our current understanding of consciousness. Picture ant colonies that have become living superorganisms capable of reshaping entire landscapes with the precision of architects and the foresight of city planners. Plant life too will undergo remarkable transformations. Trees might evolve new forms of communication and cooperation, creating forest networks of unprecedented complexity. Perhaps some plants will develop active mobility, becoming something between the plant and animal kingdoms we recognize today. Imagine forests that can actually migrate in response to climate changes, with trees that walk slowly across the landscape like enormous patient shepherds tending their ecological flocks. Climate change will undoubtedly play a major role in shaping life's future evolution. By 5 million years from now, the current human-driven climate changes will have long since played out, but their effects will still ripple through ecosystems. However, natural climate variation will continue as it has for billions of years. Our planet goes through natural warming and cooling cycles driven by changes in Earth's orbit around the Sun, variations in solar output, and the gradual movement of continents. These Milankovitch cycles, named after the Serbian mathematician who first described them, operate on timescales of tens of thousands to hundreds of thousands of years. Over our 5 million year journey, Earth will experience dozens of these natural climate fluctuations, Some periods might see ice ages more severe than any in human memory. Massive ice sheets could once again advance from the poles, covering much of North America and northern Europe under kilometers of frozen water. These ice ages would profoundly reshape the landscape, carving new valleys, creating fresh lakes, and forcing life to adapt or migrate to warmer regions. Other periods might witness greenhouse conditions warmer than anything in human experience. During these warm phases, sea levels could rise dramatically as polar ice melts, creating vast inland seas where dry land exists today. The geography of continents might become unrecognizable, with new archipelagos and island chains emerging from what we currently know as solid ground. These climate cycles will drive evolution in countless directions. Species that thrive in cold conditions will have their time to flourish and spread during ice ages, while heat-adapted creatures will dominate during warm periods. This constant environmental pressure will act like a sculptor, continually reshaping life on Earth. But climate represents just one factor in our planet's future evolution. Volcanic activity will continue playing its dramatic role in shaping landscapes and influencing global conditions. The Yellowstone supervolcano, which erupts approximately every 600,000 to 700,000 years, will likely experience several eruptions over our 5 million year time frame. Each of these events could temporarily alter global climate and create new opportunities for evolutionary change. Similarly, the East African Rift Valley continues widening at a rate of about 6 to 7 millimeters per year. Over 5 million years, this could result in the eastern portion of Africa splitting away entirely, creating a new ocean basin. The Red Sea provides a glimpse of what this might look like, the early stages of continental rifting that could eventually separate the Horn of Africa from the rest of the continent. This geological transformation would create new barriers and connections for migrating species. Animals and plants on either side of the new ocean would evolve independently, potentially leading to the development of unique ecosystems unlike anything we see today. Madagascar offers a preview of such evolutionary isolation, its long separation from mainland Africa having produced a remarkable collection of endemic species found nowhere else on Earth. The forces of erosion will also dramatically reshape our planet's surface. Mountain ranges that seem permanent and eternal to us are actually quite temporary features in geological terms. The Appalachian Mountains, once as tall as the Himalayas are today, have been worn down to gentle rolling hills over hundreds of millions of years. In 5 million years, today's youngest mountain ranges will show significant signs of this patient sculptural work. Rivers will carve new canyons and fill in old ones. The Grand Canyon, that monument to the power of flowing water, will have grown deeper and wider. Meanwhile, sediment carried by rivers will continue filling in ocean basins and creating new deltas and coastal plains. The Mississippi Delta, the Nile Delta, and similar features around the world will expand into the sea, creating fresh land for life to colonize. Earthquakes and volcanic eruptions will punctuate this slower transformation with moments of dramatic change. New islands will emerge from the ocean depths, particularly along the mid-ocean ridges where new oceanic crust constantly forms. These virgin lands will become laboratories for evolution, places where life can experiment with new forms and relationships. The Hawaiian island chain provides an excellent example of how this process works. As the Pacific Plate moves northwest over a stationary volcanic hotspot, new islands form while older ones gradually erode and sink back into the sea. In 5 million years, the Big Island of Hawaii will have moved far to the northwest, and entirely new volcanic islands will have emerged to take its place. Such newly formed islands become crucibles of evolution. The first organisms to arrive typically come by chance, carried by wind, water, or other animals. With few competitors and many empty ecological niches to fill, these pioneer species often evolve rapidly into forms dramatically different from their ancestors. The process that created the unique flora and fauna of places like the Galapagos Islands and Hawaii will repeat countless times over our 5 million year journey. Ocean currents will also undergo significant changes as continents continue their slow dance around the globe. The Gulf Stream, that massive river of warm water that moderates Western Europe's climate, depends on the current configuration of continents and ocean basins. As the Atlantic widens and the geography of surrounding landmasses changes, this current could weaken, shift course, or even shut down entirely. Such changes in ocean circulation patterns would have profound effects on global climate and marine ecosystems. Regions that currently enjoy mild temperatures due to warm ocean currents might experience much colder conditions. Conversely, areas currently cooled by cold currents might become significantly warmer. The deep ocean, that vast realm we're only beginning to explore today, will likely reveal even more of its secrets over the next 5 million years. As life continues evolving in the crushing depths, strange new creatures will emerge, perhaps developing forms of intelligence and social organization, unlike anything in the sunlit surface waters. Hydrothermal vents, those oases of life in the deep ocean desert, will continue serving as evolutionary laboratories. The unique chemical environment around these underwater geysers supports ecosystems unlike anywhere else on Earth. Over millions of years, the life forms around these vents might evolve into something truly alien, organisms that push the boundaries of what we consider possible for carbon-based life. Some scientists speculate that deep ocean life might even evolve primitive forms of technology, using the unique chemistry of their environment to create tools and structures. Imagine colonies of deep-sea organisms that have learned to manipulate mineral deposits around hydrothermal vents, creating complex structures that serve as both habitat and technology. The relationship between life and geology will become even more intertwined over these vast timescales. Life doesn't just respond to geological changes, it actively participates in shaping the planet's surface and atmosphere. Plants and microorganisms weather rocks, creating soil and altering the chemical composition of the atmosphere and oceans. Coral reefs represent one of the most dramatic examples of life-shaping geology. These massive structures, built entirely by tiny marine organisms, can be seen from space and influence ocean currents and coastal processes. Over 5 million years, entirely new reef systems will form while others disappear, creating and destroying underwater mountain ranges through purely biological processes. Forest ecosystems perform similar geological work on land. Tree roots break apart rocks, while falling leaves create soil and alter local drainage patterns. Over millions of years, forests can literally move mountains, breaking them down grain by grain and transporting the resulting sediment to distant oceans. Even the atmosphere itself remains a dynamic, living system. The oxygen we breathe exists only because of billions of years of photosynthetic activity by plants and algae. The carbon dioxide levels that influence global climate depend partly on the activity of countless microorganisms in soil and ocean sediments. Over 5 million years, these biological processes will continue reshaping our planet's atmosphere. If photosynthetic organisms evolve new efficiencies or expand into previously uninhabitable environments, atmospheric composition could change significantly. Similarly, if new forms of life evolve that consume or produce different gases, the very air future organisms breathe might have a different chemical signature than today's atmosphere. These changes will create opportunities for life to colonize previously inaccessible regions. During warm periods, plants and animals will spread northward and southward toward the poles. Antarctica, currently hidden beneath kilometers of ice, might experience periods of partial thaw that reveal ancient mountain ranges and valleys. Life that survives in the rare ice-free areas of Antarctica today might expand and diversify during these warmer interludes, creating unique polar ecosystems unlike anything currently existing on Earth. The Arctic presents equally fascinating possibilities. As sea ice diminishes during warm periods, new migration routes will open for marine life. Whales that currently can't travel between the Atlantic and Pacific through the Arctic Ocean will gain new pathways, potentially leading to increased genetic mixing and the evolution of new populations. Terrestrial life in the Arctic will face both challenges and opportunities. The thawing of permafrost will release vast amounts of carbon and nutrients locked in frozen soil, potentially creating bursts of plant growth and ecosystem productivity. However, The changing ground conditions will also alter drainage patterns and soil stability, forcing both plants and animals to adapt to new conditions. Some Arctic species might evolve remarkable flexibility, developing the ability to dramatically alter their behavior and physiology in response to changing conditions. Imagine Arctic foxes that can adjust their fur color, thickness, and even their body size seasonally in response to environmental cues, or Arctic plants that have evolved the ability to grow rapidly during brief warm periods, then enter extended dormant states when conditions become harsh again. The interface between ice and water will continue providing unique evolutionary opportunities. Organisms that live at the edges of glaciers and sea ice experience some of the most variable conditions on Earth. These environments select for incredible adaptability and resilience. Over millions of years, life in these transitional zones might evolve forms of flexibility that allow rapid adaptation to changing conditions. As we continue our journey through deep time, it's worth considering how the relationship between different species will evolve. Symbiosis, the close cooperation between different organisms, has been one of the major drivers of complexity in life's history. The cells that make up all complex organisms today, including humans, evolved through ancient symbiotic relationships between simpler cells. Over the next 5 million years, we might witness the evolution of entirely new forms of symbiosis. Perhaps some plants and animals will develop partnerships so intimate that they essentially become single organisms with multiple components. Imagine trees that form permanent partnerships with specific bird species, with the birds providing protection and seed dispersal in exchange for specialized fruits that meet all their nutritional needs. Marine environments might see the evolution of even more complex symbiotic relationships. Coral reefs already demonstrate remarkable cooperation between animals, plants, and microorganisms. Over millions of years, these partnerships might become so sophisticated that entire reef systems function as single, massive organisms, with specialized regions performing different functions like organs in a body. Over 5 million years, this evolutionary arms race will produce adaptations we can barely imagine. Perhaps some prey species will evolve forms of camouflage so sophisticated they can mimic not just their surroundings, but other organisms entirely. Imagine small mammals that can alter their appearance so completely they can masquerade as plants, rocks, or even other animal species. Predators might respond by developing equally remarkable hunting adaptations. Some might evolve enhanced sensory abilities that can detect prey regardless of camouflage. Others might develop cooperative hunting strategies of unprecedented complexity, with different individuals playing specialized roles in elaborate hunting sequences. The evolution of intelligence represents one of the most intriguing aspects of life's future development. Intelligence has evolved independently multiple times in Earth's history, appearing in vertebrates like primates and dolphins, in cephalopods like octopi, and even in some invertebrates like bees and ants. Over 5 million years, intelligence might evolve in lineages we wouldn't expect today. Perhaps some reptile species will develop problem-solving abilities rivaling those of mammals. Maybe certain bird families will evolve forms of abstract thinking that surpass human capabilities in specific areas. Some ant and bee colonies already display forms of collective decision-making that surpass the abilities of individual insects. Over millions of years, these collective intelligences might become incredibly sophisticated, perhaps developing their own forms of culture, art, and technology that operate on completely different principles from human civilization. Whales and dolphins already display remarkable cognitive abilities, including self-awareness, complex communication, and cultural transmission of knowledge. Over 5 million years, these abilities might develop into something approaching technological civilization, but one based on sound, social cooperation, and manipulation of ocean currents, rather than tools and fire. As we contemplate these vast spans of time and change, it's humbling to realize that 5 million years represents just a tiny fraction of Earth's total history. Our planet has existed for about 4.6 billion years, meaning our journey covers just over 1/10 of 1% of Earth's existence. The fossil record tells us that 5 million years is enough time for entirely new groups of organisms to evolve and diversify. It's long enough for mountain ranges to rise and fall, for ocean basins to open and close, and for the climate to cycle through numerous dramatic changes. Yet it's also important to remember that some aspects of our planet will remain remarkably stable over this time frame. The basic laws of physics and chemistry that govern how matter and energy interact won't change. The fundamental processes of evolution, though they might produce surprising results, will continue operating according to the same principles they always have. The sun will continue shining with only minor variations in output. While it's gradually growing brighter over geological time, the change over 5 million years will be barely perceptible. The moon will continue orbiting Earth, though it will have moved slightly further away due to tidal interactions. The day will have grown imperceptibly longer as Earth's rotation gradually slows. These stable elements provide the stage upon which all the dramatic changes of life and geology will play out. They remind us that even as everything changes, certain fundamental aspects of our cosmic environment remain constant, providing the reliable framework that makes complex development possible. This balance will continue shaping our planet's future. Periods of rapid change will alternate with times of relative stability, creating opportunities for both innovation and consolidation. Life will continue finding ways to exploit new opportunities while preserving successful adaptations from the past. The story of the next 5 million years will be written in the language of adaptation and change, but also in the vocabulary of continuity and persistence. Bacteria and archaea, the simplest forms of life, will likely remain recognizably similar to their current forms. These organisms have already perfected strategies for survival that have worked for billions of years. Their basic cellular machinery is so fundamental to life that dramatic changes are unlikely. However, even these simple organisms might surprise us. They might evolve new metabolic pathways that allow them to exploit energy sources currently unavailable to life. Perhaps some bacteria will learn to harvest energy directly from radioactive decay, or develop ways to extract usable energy from gravitational fields. Plants will certainly undergo remarkable transformations, but they'll still likely be recognizable as photosynthetic organisms that convert sunlight into chemical energy. However, the ways they accomplish this fundamental task might become incredibly sophisticated. Some plants might evolve the ability to actively modify their local environment to suit their needs. Perhaps certain species will develop ways to alter soil chemistry, local humidity, or even microclimate conditions to create optimal growing conditions for themselves and their offspring. The relationship between plants and fungi will likely become even more sophisticated than it is today. But most plants already form partnerships with soil fungi that help them absorb nutrients and water. Over the next 5 million years, mammals might push the boundaries of their adaptability even further. Perhaps some lineages will evolve the ability to survive in space, developing adaptations that allow them to live in the vacuum and radiation of the cosmic environment. While this might sound impossible, life has already shown an incredible ability to survive in environments once thought completely hostile to living organisms. Birds, already masters of three-dimensional movement, might evolve even more sophisticated flight capabilities. Some species might develop the ability to fly at much higher altitudes, perhaps even reaching the edge of space. Others might evolve underwater flight capabilities, becoming as comfortable in the ocean depths as they are in the atmosphere. The evolution of bird intelligence might produce species capable of complex technological manipulation. The boundary between reptiles and birds, already blurred by evolutionary history, might become even more indistinct. Perhaps some reptile lineages will independently evolve flight, while some birds might lose their flight capabilities and become more reptile-like in their ecology. Amphibians face particular challenges due to their dependence on both aquatic and terrestrial environments. However, this same dependence might also provide unique evolutionary opportunities. Some amphibians might evolve the ability to remain active during periods when their breeding habitats are unavailable, perhaps developing forms of extended dormancy that allow them to survive years of drought. Fish will continue diversifying in the vast oceanic environment. The deep ocean, still largely unexplored today, will likely reveal new forms of fish life adapted to extreme conditions. Some deep-sea fish might evolve forms of bioluminescence, so sophisticated they can create complex visual displays, perhaps even developing underwater forms of art or communication that rival human creativity. Freshwater fish face the challenge of changing river and lake systems as continental drift and climate change alter drainage patterns. Some species might evolve remarkable mobility, developing the ability to move between different water systems during brief periods when they're connected by flooding or other events. Invertebrates, representing the vast majority of animal species, will likely undergo the most dramatic evolutionary changes. Their shorter generation times and simpler body plans allow for more rapid evolutionary change than is possible for larger, longer-lived organisms. Insects might evolve forms of collective behavior that blur the line between individual organisms and superorganisms. Imagine termite colonies that have become so sophisticated in their construction abilities that they create underground cities, rivaling human urban centers in complexity. Some insect lineages might evolve new forms of metamorphosis, perhaps developing multiple adult forms adapted to different seasonal conditions or ecological roles. Picture butterflies that can choose between different adult forms depending on environmental conditions during their development. Spiders and other arachnids might push the boundaries of web construction and hunting strategies. Some species might evolve the ability to create webs that actively manipulate their environment, perhaps even developing primitive forms of agriculture by cultivating specific prey species. Marine invertebrates offer perhaps the greatest potential for evolutionary surprises. The octopi and their relatives have already demonstrated remarkable intelligence and adaptability. Over millions of years, they might evolve forms of technology based on biological manipulation rather than tool use. Imagine cephalopods that have learned to cultivate specific types of algae or bacteria, using these organisms as living tools to modify their environment. Or picture squid that have developed forms of cooperative behavior so sophisticated they can coordinate the activities of entire ocean regions. Coral reefs might evolve into even more complex ecosystems, with individual coral polyps developing specialized functions within the larger reef community. Some corals might evolve the ability to actively manage water quality and nutrient flow throughout the reef system, creating vast underwater gardens of incredible beauty and productivity. The microscopic world will continue driving many of the larger changes we observe. Bacteria and other microorganisms evolve much more rapidly than larger organisms, potentially developing new capabilities every few thousand years rather than over millions of years. Some bacteria might evolve the ability to break down entirely new types of materials, perhaps helping to clean up industrial pollutants or even processing materials we haven't invented yet. Others might develop new forms of symbiosis with larger organisms, creating partnerships that enhance the capabilities of both partners. Viruses, existing at the boundary between living and non-living matter, might play crucial roles in horizontal gene transfer between different species. This process could accelerate evolution by allowing successful adaptations to spread between unrelated organisms much more quickly than traditional inheritance would permit. The interaction between all these evolving organisms will create ecosystems of unprecedented complexity and beauty. Food webs will develop new interconnections and dependencies, creating stable yet dynamic networks of energy and material flow. Some ecosystems might evolve forms of self-regulation so sophisticated they can maintain stable conditions even in the face of external disruptions. Picture grasslands that actively manage their own water cycles, or forests that coordinate their response to climate variations across continental scales. The relationship between terrestrial and marine ecosystems will likely become even more interconnected. Rivers and streams that connect land and sea might become corridors for new forms of organisms that spend parts of their lives in both environments. Coastal ecosystems, where land meets sea, will continue serving as laboratories for evolutionary innovation. These dynamic environments, constantly changing due to tides, storms, and seasonal variations, select for incredible adaptability and resilience. Some organisms might evolve the ability to take advantage of multiple ecosystems simultaneously, perhaps developing life cycles that span terrestrial, freshwater, and marine environments. This could lead to the evolution of organisms with capabilities we can barely imagine today. The polar regions, as they cycle through periods of ice coverage and ice-free conditions, will provide unique evolutionary opportunities. Organisms adapted to these extreme environments might develop forms of hibernation or dormancy so sophisticated they can survive thousands of years of unfavorable conditions. Desert ecosystems will continue pushing the boundaries of what's possible for life in extreme conditions. Some desert organisms might evolve the ability to survive entirely without external water sources, perhaps developing internal recycling systems so efficient they approach theoretical limits of water conservation. Mountain ecosystems, as they rise and fall over geological time, will create islands of unique conditions that promote rapid evolutionary change. Organisms, isolated on mountain peaks, might evolve into new species much more quickly than their relatives in more stable environments. Some underground organisms might evolve the ability to tap directly into geothermal energy sources, creating ecosystems powered by the heat of Earth's interior rather than sunlight. These deep biospheres might develop forms of life so different from surface organisms that they represent entirely separate evolutionary experiments. As we contemplate these vast possibilities, it's worth reflecting on the role of extinction in shaping evolution's future course. Extinction events, both large and small, create opportunities for surviving organisms to diversify and explore new evolutionary possibilities. Over 5 million years, Earth will certainly experience multiple extinction events of various scales. Some might be caused by volcanic eruptions, asteroid impacts, or other catastrophic events. Others might result from more gradual changes in climate, ocean chemistry, or atmospheric composition. Each extinction event will be followed by a period of rapid evolutionary radiation as surviving organisms adapt to fill empty ecological niches. These recovery periods often produce some of the most dramatic evolutionary innovations in Earth's history. The organisms that survive extinction events often share certain characteristics, such as small size, rapid reproduction, and broad dietary flexibility. Over millions of years, these survival traits might become even more sophisticated, with some organisms evolving the ability to sense and prepare for environmental catastrophes. Climate will continue playing a major role in driving evolutionary change. Natural climate variations operate on many different timescales, from annual seasonal cycles to million-year orbital variations. Each of these cycles creates different selective pressures and evolutionary opportunities. The gradual increase in solar brightness over geological time will eventually require life to develop new strategies for managing heat and radiation. Some organisms might evolve enhanced radiation resistance, while others might develop more efficient ways to reflect or dissipate excess energy. Ocean chemistry will also undergo significant changes over our 5 million year timeframe. The gradual acidification of seawater, changes in nutrient availability, and variations in ocean circulation patterns will all influence marine evolution. Some marine organisms might evolve the ability to actively modify local water chemistry to create more favorable conditions for themselves. The relationship between life and Earth's magnetic field presents another fascinating area for future evolution. Earth's magnetic field, which protects the planet from harmful cosmic radiation, undergoes periodic reversals where magnetic north and south switch places. During these magnetic reversals, which occur roughly every 200,000 to 300,000 years on average, the protective magnetic shield weakens significantly for periods that can last several thousand years. Over our 5 million year journey, Earth will likely experience 15 to 20 such reversals, each creating unique evolutionary pressures. Some organisms might evolve enhanced resistance to cosmic radiation during these vulnerable periods. Perhaps certain bacterial lineages will develop more sophisticated DNA repair mechanisms, or some animals might evolve behaviors that help them seek shelter during times of increased radiation exposure. Birds and other animals that navigate using magnetic fields will face particular challenges during these reversals. Some species might evolve backup navigation systems based on other environmental cues, while others might develop enhanced sensitivity to the weakened magnetic signals that persist during reversals. The aurora, those magnificent curtains of light that currently dance near Earth's magnetic poles, will behave very differently during magnetic reversals. Instead of being confined to polar regions, auroral displays might appear at all latitudes, creating spectacular light shows visible from anywhere on Earth. Life forms that have evolved to take advantage of these displays, perhaps using them for timing reproductive cycles or migration patterns, will need to adapt to their changed behavior. Some organisms might even evolve the ability to sense and respond to these magnetic changes directly. Picture migrating animals that can detect the early signs of an approaching magnetic reversal and adjust their behavior accordingly, perhaps altering their reproductive timing to ensure their offspring are born during periods of magnetic stability. The interaction between solar activity and Earth's magnetic field adds another layer of complexity to our planet's future. The Sun goes through 11-year cycles of magnetic activity, with periods of intense solar storms alternating with quieter phases. Over millions of years, these cycles might change in intensity or duration, creating new patterns of space weather that life will need to navigate. During particularly intense solar storms, even Earth's normal magnetic field provides limited protection. Organisms living at high altitudes or in polar regions already experience higher levels of cosmic radiation. Over evolutionary time, these populations might develop specialized adaptations that could prove valuable if space weather becomes more severe. Some scientists speculate that certain organisms might even evolve the ability to harness geomagnetic energy directly. While this might sound impossible, life has already surprised us by evolving the ability to use many energy sources once thought inaccessible to biological systems. Perhaps some future organisms will develop biological structures that can detect and utilize the electrical currents generated by Earth's magnetic field. The relationship between life and geology will become even more intimate over our 5 million year time frame. We already know that living organisms have profoundly shaped Earth's surface and atmosphere. The oxygen we breathe exists only because of billions of years of photosynthetic activity. Limestone cliffs and coral reefs represent massive geological structures built entirely by living organisms. Over the next 5 million years, life might begin engineering geological processes on even grander scales. Imagine plant communities that have evolved the ability to direct the flow of rivers by strategic placement of their root systems, or microbial communities that actively manage the chemical composition of entire mountain ranges through their metabolic activities. Some organisms might evolve symbiotic relationships with geological processes themselves. Picture bacteria that have formed partnerships with mineral-forming processes, creating living rocks that can grow, reproduce, and evolve. These geobiological hybrids might blur the line between the living and non-living worlds in ways we can barely imagine. The deep subsurface environment, extending kilometers below Earth's surface, will likely reveal new forms of life over our extended time frame. We're already discovering that this deep biosphere hosts vast communities of microorganisms living in conditions once thought impossible for life. Over millions of years, these deep communities might evolve into complex ecosystems completely independent of surface conditions. Some deep organisms might develop the ability to use radioactive decay as an energy source, creating ecosystems powered by the slow nuclear decay of elements in Earth's crust. Others might learn to harvest energy from the pressure and heat of deep burial, or develop ways to utilize the chemical energy stored in mineral structures. These deep ecosystems might eventually rival surface ecosystems in their complexity and diversity. The interface between Earth's biosphere and space will become increasingly important as our planet continues its journey through the cosmos. While Earth travels through space, it encounters varying densities of cosmic dust, different intensities of cosmic radiation, and occasional close approaches to other celestial bodies. Over 5 million years, Our solar system will complete roughly 25 orbits around the center of the Milky Way galaxy. During this galactic journey, we'll pass through different regions of space with varying properties. Some areas might expose Earth to higher levels of cosmic radiation, while others might provide more protection. Life might evolve sophisticated mechanisms for detecting and responding to these changing cosmic conditions. Perhaps some organisms will develop internal biological calendars that track not just seasonal and annual cycles, but the much longer cycles associated with our galaxy's rotation. The possibility of impacts from asteroids or comets adds another element of unpredictability to our planet's future. While major impacts are relatively rare, smaller events occur much more frequently. Over 5 million years, Earth will certainly experience numerous smaller impacts that could influence local and regional ecosystems. The dust and debris thrown into the atmosphere by impacts can temporarily alter global climate conditions. Organisms that can quickly adapt to these short-term climate changes might gain significant evolutionary advantages. Picture plants that can rapidly switch between different photosynthetic strategies depending on light availability, or animals that can enter extended dormant states during periods of atmospheric disruption. As we venture deeper into our 5 million year journey, the cumulative effects of all these individual changes will create transformations that go far beyond the sum of their parts. Small changes in climate, ocean chemistry, continental positions, and evolutionary adaptations will interact in complex ways, potentially producing entirely unexpected outcomes. The concept of emergent properties, where complex systems develop characteristics that couldn't be predicted from understanding their individual components, will likely play a major role in shaping our planet's future. Just as no one could have predicted the emergence of human civilization by studying individual neurons, the Earth system 5 million years from now might display properties and behaviors that we can't anticipate from our current understanding. One fascinating possibility is the emergence of planetary-scale self-regulation mechanisms. We already see hints of this in systems like the global carbon cycle, where biological and geological processes work together to maintain relatively stable atmospheric conditions over long time periods. Over millions of years, these regulatory mechanisms might become much more sophisticated and responsive. Perhaps the global ecosystem will evolve forms of feedback control that can actively respond to external disruptions, maintaining stable conditions, even in the face of significant challenges. This could lead to a form of planetary intelligence, where the Earth system as a whole develops the ability to sense, process information, and respond to changing conditions. While this might sound like science fiction, remember that individual organisms are essentially collections of cells that have evolved sophisticated coordination mechanisms. Perhaps similar coordination could emerge at planetary scales. The role of information and communication in evolution will likely become increasingly important over our extended time frame. Life has always depended on the ability to store, transmit, and process information, from the genetic code that passes traits between generations to the complex communication systems used by social animals. Over 5 million years, organisms might evolve information processing capabilities that rival or exceed our current technology. Some species might develop biological computers based on neural networks, allowing them to perform complex calculations and predictions about their environment. Others might evolve sophisticated communication systems that allow real-time coordination across vast distances. Imagine forest networks where individual trees can instantaneously share information about resource availability, threats, or opportunities across entire continents. The boundary between individual organisms and larger collective systems might become increasingly blurred. We already see this in colonies of social insects, where individual ants or bees function more like cells in a larger organism than as independent creatures. Over millions of years, this trend toward greater integration might produce macroorganisms of incredible size and complexity. Picture forest systems that function as single coordinated entities, with individual trees serving specialized roles like organs in a body. Or imagine ocean ecosystems where different species have become so interdependent they essentially form single ocean-spanning organisms. The evolution of consciousness presents one of the most intriguing mysteries for our planet's future. Consciousness, the subjective experience of being aware, remains one of the least understood phenomena in biology. We don't fully understand how it arises from brain activity, why it evolved, or what forms it might take in other organisms. Over 5 million years, consciousness might evolve in directions we can't currently imagine. Perhaps some organisms will develop forms of awareness that extend beyond individual bodies, creating collective consciousnesses that span entire ecosystems. Others might evolve time-dilated consciousness, experiencing subjective time at rates very different from their biological processes. Imagine organisms that experience years of subjective time during brief moments of biological activity, or conversely, creatures whose consciousness operates so slowly that they experience entire seasons as brief moments. The relationship between consciousness and the physical environment might also evolve in remarkable ways. Some organisms might develop the ability to extend their awareness into their surroundings, essentially becoming conscious of environmental conditions far from their physical bodies. This could lead to forms of ecological consciousness, where individual organisms become aware not just of their own needs and states, but of the health and condition of entire ecosystems. Such organisms might function as environmental stewards, actively working to maintain the health of the larger systems they're conscious of. The question of whether artificial and biological intelligence will merge over our 5 million year time frame adds another layer of complexity to these speculations. If technological civilization survives and continues advancing, the distinction between natural and artificial intelligence might become meaningless. Future organisms might incorporate both biological and technological components in ways that enhance their capabilities beyond what either system could achieve alone. These hybrid intelligences might develop capabilities for space travel, deep ocean exploration, or survival in extreme environments that would be impossible for purely biological organisms. The exploration of other planets and moons in our solar system might also play a role in terrestrial evolution. If life from Earth spreads to other worlds, the unique conditions on those worlds will drive evolution in new directions. Some of these extraterrestrial adaptations might eventually find their way back to Earth through natural processes or conscious reintroduction. Mars, with its thin atmosphere and cold temperatures, might select for organisms with extreme cold tolerance and efficient resource utilization. The moons of Jupiter and Saturn, with their subsurface oceans, might become laboratories for the evolution of life adapted to high-pressure aquatic environments with unusual chemistry. These off-world evolutionary experiments could provide Earth's biosphere with entirely novel genetic resources and adaptive strategies. The return of space-adapted organisms to Earth might introduce new capabilities and perspectives that enhance the resilience and complexity of terrestrial ecosystems. The timescales we're contemplating, 5 million years, represent periods during which entirely new forms of matter and energy manipulation might become possible for biological systems. Life has already evolved the ability to harness chemical energy, electromagnetic radiation, and even some forms of nuclear processes through radioactive metabolism. Future organisms might develop the ability to manipulate matter at the atomic level, essentially evolving biological nanotechnology. This could allow for self-repair mechanisms of unprecedented sophistication, or the ability to transform simple elements into complex organic compounds with remarkable efficiency. Some organisms might even evolve ways to utilize quantum mechanical effects for information processing or energy manipulation. While quantum biology is still a new field, we're already discovering that some organisms use quantum effects for processes like photosynthesis and navigation. Over millions of years, these quantum biological systems might become much more sophisticated, perhaps allowing organisms to perform computations or sense environmental conditions in ways that classical physics wouldn't permit. This could lead to forms of biological technology that operate on principles we're only beginning to understand. The role of symbiosis in driving these future developments cannot be overstated. Throughout Earth's history, many of the most significant evolutionary innovations have resulted from different organisms forming intimate partnerships. The cells that make up all complex life today evolved through ancient symbiotic mergers between simpler organisms. These symbiotic superorganisms might be able to occupy ecological niches that would be impossible for any single species. Imagine partnerships between photosynthetic and chemosynthetic organisms that can thrive equally well in sunlight and in deep ocean environments, or collaborations between flying and swimming organisms that can seamlessly transition between aerial and aquatic lifestyles. The genetic mechanisms underlying such complex partnerships might themselves evolve in remarkable directions. We're already discovering that horizontal gene transfer, the direct sharing of genetic material between unrelated organisms, is much more common than previously thought. Over millions of years, this genetic sharing might become so sophisticated that the traditional concept of species boundaries becomes meaningless. Instead of distinct species, we might see genetic networks where useful adaptations can rapidly spread throughout entire ecosystems. This could lead to forms of evolutionary acceleration, where beneficial mutations that arise in one organism quickly become available to many others. Such systems might be able to adapt to environmental changes much more rapidly than traditional evolutionary mechanisms would allow. The mathematics of population genetics suggests that 5 million years provides enough time for completely novel forms of genetic organization to evolve. We might see the emergence of organisms with multiple independent genetic systems, each optimized for different functions or environmental conditions. Some organisms might evolve modular genetic architectures, where different parts of their genome can be activated or deactivated in response to environmental cues. This could allow single organisms to essentially transform into different species depending on the conditions they encounter. Others might develop genetic systems based on different chemical foundations than the DNA and RNA that currently dominate terrestrial life. While these alternative genetic systems would need to be compatible with existing biochemistry, they might offer advantages for information storage, processing, or transmission that could prove valuable in future environments. The relationship between genetics and development, how genes guide the growth of organisms from single cells to complex adults, will likely undergo remarkable transformations over our extended time frame. We're already discovering that this relationship is much more flexible and dynamic than once thought. Some might even evolve the ability to undergo multiple developmental phases throughout their lives, essentially becoming different organisms at different life stages. This could allow single species to occupy multiple ecological niches simultaneously, with different life stages specialized for different functions. Over 5 million years, organisms might evolve sensory capabilities that allow them to detect phenomena we can barely measure with our most sophisticated instruments. Perhaps some creatures will develop the ability to sense gravitational variations, allowing them to detect the presence of massive objects at great distances. Others might evolve quantum sensors that can detect individual particles or photons, providing them with information about their environment at levels of detail currently available only to our most advanced scientific equipment. Such hypersensitive organisms might be able to predict environmental changes long before they become apparent through conventional means. The integration of multiple sensory modalities might also reach new levels of sophistication. Some organisms might develop unified sensory systems that process information from dozens of different sources simultaneously, creating rich, multidimensional perceptions of their environment that we can barely imagine. These enhanced sensory capabilities might also extend across time, with some organisms evolving the ability to integrate information across extended time periods. Picture creatures that can sense not just current environmental conditions, but trends and patterns that extend across seasons, years, or even decades. The locomotion strategies of future organisms will likely diversify in remarkable directions as well. Life has already evolved flight, swimming, running, climbing, and burrowing. Over millions of years, entirely new forms of movement might emerge. Some organisms might evolve the ability to manipulate electromagnetic fields for propulsion, essentially developing biological magnetic levitation systems. Others might learn to use sound waves or chemical jets for movement, or develop ways to manipulate surface tension and fluid dynamics for more efficient travel through liquid environments. The boundaries between different forms of locomotion might also blur, with organisms developing seamless transitions between flying, swimming, and terrestrial movement. Picture creatures that move through air, water, and solid substrates with equal facility, using different mechanisms optimized for each medium. Some organisms might even evolve forms of movement that take advantage of planetary rotation, tidal forces, or other large-scale physical phenomena. While this might sound impossible, remember that many organisms already time their activities to take advantage of daily and seasonal cycles. The reproductive strategies of future life will certainly diversify beyond our current understanding. Sexual reproduction, with its mixing of genetic material from two parents, has been incredibly successful throughout Earth's history. However, many organisms have evolved alternatives that might become even more sophisticated over extended time periods. Some species might evolve reproductive systems that can switch between sexual and asexual reproduction depending on environmental conditions. Others might develop multi-parent reproduction, where genetic material from 3, 4, or even more individuals combines to create offspring. The timing and triggering of reproduction might also become much more sophisticated. Some organisms might evolve the ability to predict optimal reproductive conditions years or decades in advance, timing their reproduction to coincide with predicted environmental opportunities. Others might develop reproductive strategies that span multiple generations, with parents, grandparents, and great-grandparents all contributing to the care and guidance of offspring. Such extended family systems might allow for the accumulation and transmission of knowledge and skills across much longer time periods than current organisms can achieve. Some organisms might evolve the ability to halt or reverse aging processes, essentially achieving biological immortality. Others might develop cyclical life processes, where they periodically regenerate their entire body, maintaining the same identity while completely renewing their physical structure. The boundary between individual death and continuation through offspring might also become blurred. Some organisms might evolve forms of genetic and mimetic continuity so sophisticated that individual death becomes less meaningful, with essential information and identity persisting through subsequent generations. These changes in aging and death would have profound implications for evolution itself. If individual organisms can survive for extremely long periods, they might accumulate knowledge and adaptations throughout their extended lifespans in ways that could accelerate evolutionary change. The social structures of future organisms present equally fascinating possibilities. We already see remarkable social complexity in organisms ranging from bacteria to whales. Over millions of years, these social systems might evolve capabilities that rival or exceed human civilization in their sophistication. Some species might develop social organizations so complex they function as collective intelligences, with individual organisms serving specialized roles in larger thinking systems. Others might evolve forms of social coordination that allow them to manage resources and respond to challenges across continental or even global scales. The communication systems that enable these social structures will likely become incredibly sophisticated. Some organisms might develop languages with grammatical complexity and expressive power that surpass human language. Others might evolve multimodal communication systems that use sound, light, chemistry, and even quantum effects simultaneously. These advanced communication systems might also bridge species boundaries, allowing different types of organisms to coordinate their activities in ways that benefit entire ecosystems. Picture interspecies communication networks that allow forests, grasslands, and aquatic systems to coordinate their responses to environmental changes. The concept of culture, the transmission of learned behaviors and knowledge across generations, might also expand far beyond its current manifestations. While we typically associate culture with human societies, many other species already display cultural transmission of information. Over millions of years, these cultural systems might become so sophisticated they essentially constitute non-genetic inheritance systems. Some organisms might develop cultural knowledge that accumulates across thousands of generations, creating libraries of environmental and behavioral information that dwarf the genetic information stored in their DNA. Such cultural systems might also become increasingly important for rapid adaptation to changing conditions. While genetic evolution operates over many generations, cultural evolution can occur much more rapidly, allowing organisms to adapt to new challenges within single lifetimes. The tools and technologies that organisms might develop present another area of fascinating speculation. While we typically think of tool use as primarily human, many other species already create and use tools for various purposes. Over extended time periods, some organisms might develop technological capabilities that rival human achievements. However, these biological technologies would likely operate on very different principles from human technology, perhaps emphasizing self-repair, self-reproduction, and integration with natural systems. Imagine organisms that have learned to cultivate and shape other species as living tools, creating biological technologies that can grow, adapt, and evolve to meet changing needs. Or picture creatures that have developed ways to manipulate their environment so precisely they can essentially program ecological systems to perform specific functions. The energy sources that future organisms might learn to exploit will likely extend far beyond the photosynthesis and chemical metabolism that dominate today's biosphere. We're already discovering organisms that can use radioactive decay, electrical currents, and other exotic energy sources. Over millions of years, some organisms might evolve the ability to harvest energy from gravitational fields, magnetic fields, or even more exotic physical phenomena. This could allow life to thrive in environments and conditions that would be completely impossible for current organisms. The waste products and byproducts of metabolism might also become resources for other organisms in ways we can't currently imagine. Future ecosystems might evolve closed-loop systems where every waste product from one organism becomes a valuable resource for another, creating cycles of incredible efficiency and sustainability. These highly integrated systems might also develop the ability to actively manage their own environmental conditions, essentially creating self-regulating biospheres within larger ecosystems. Such systems might be able to maintain optimal conditions for their member organisms, even in the face of significant external environmental changes. The spatial scales over which organisms operate might also expand dramatically over our 5 million year timeframe. Picture organisms that can coordinate activities across entire ocean basins or forest networks, that manage resources and information across multiple continents. Such planetary-scale organisms might develop perspectives and capabilities that transcend anything we can currently imagine. The temporal scales over which organisms operate present equally intriguing possibilities. Some future species might evolve biological processes that operate over centuries or millennia, allowing them to plan and coordinate activities across timescales that dwarf human planning horizons. Others might develop the ability to compress complex activities into incredibly brief time periods, essentially creating biological systems that can accomplish in seconds what currently requires years or decades. Such time-flexible organisms might be able to take advantage of brief opportunities that other species can't even detect. As we near the end of our 5 million year journey, it's worth reflecting on the profound uncertainty that surrounds all these speculations. The future is inherently unpredictable, and the further into the future we try to look, the more uncertain our predictions become. However, this uncertainty itself is part of what makes the future so fascinating. The history of life on Earth is filled with unexpected innovations and surprising developments that no one could have predicted. The emergence of photosynthesis, the evolution of multicellular life, the development of consciousness, all represent fundamental innovations that transform the entire biosphere. The one certainty is that change will continue. The Earth of 5 million years from now will be as different from today's world as today's Earth differs from the Pliocene epoch 5 million years ago. New continents will have formed, new species will have evolved, new ecosystems will have emerged, and new forms of life will have discovered ways to thrive in conditions we might consider impossible. Yet through all this change, the fundamental processes that drive evolution and shape our planet will continue operating according to the same basic principles they always have. Natural selection will continue favoring organisms that are well adapted to their environments. Continental drift will continue reshaping the surface of our planet. Climate will continue changing in response to astronomical and geological forces. These enduring processes provide the stable foundation upon which all the dramatic changes of evolution play out. They remind us that while everything changes, change itself follows predictable patterns and principles that we can study and understand. As we conclude our journey through deep time, perhaps the most important lesson is one of humility. The future holds possibilities so vast and varied that our current knowledge and imagination can only hint at what lies ahead. 5 million years is enough time for transformations that would render our world utterly unrecognizable. Yet it's also brief enough that the basic laws of physics and chemistry will remain constant. Life will continue finding ways to survive, adapt, and flourish in whatever conditions the future brings. The creativity and resilience that have carried life through billions of years of Earth's history will continue driving evolution toward outcomes we can't predict, but can be certain will be remarkable. The story of the next 5 million years remains unwritten, waiting to unfold through the patient work of countless generations of organisms adapting, evolving, and discovering new ways to participate in the grand experiment of life on Earth. It's a story that will be written in the language of genetics and geology, of climate and chemistry, of adaptation and innovation. And perhaps somewhere in that future story, there will be conscious beings like ourselves, looking back through deep time and marveling at the journey that brought them to their present moment, while simultaneously gazing forward into their own uncertain but undoubtedly remarkable future. The dance between stability and change, between predictability and surprise, between the known and the unknowable, will continue shaping our planet's destiny. 5 million years from now, Earth will still be orbiting the same sun, still turning on its axis, still supporting the grand adventure of life. But the details of that adventure, the specific forms it will take, and the particular wonders it will create, remain among the most beautiful mysteries awaiting discovery in the vast library of time.